In this video, we're going to see how to make distributions from quantitative data when we have numerical data. We're going to also talk about concepts like relative frequency and cumulative frequency, and we're going to see how to measure them, how to compute them. And we're also going to talk about the histogram, which is the graphical display of distribution tables. For that, we're going to use the data file audit data. Have the data file here. We have some numbers. These are the number of days that the year-end audit takes for the company. And we do have these numbers for 20 different companies, and we want to build the distribution here. When we have quantitative data, building the distribution is a little more difficult and a little bit more challenging than when we're working with categorical data. In categorical data, the categories are already defined. Here, we're just working with numbers. And as you can see here, we are working with numbers that are, ranged from, let's say, 12. 12 is the minimum number. 33, we have numbers, integer numbers between 12 and 33. And we have to make it in different groups or bins, as we call it for the quantitative data. We're gonna create a few bins. So before we go ahead and build the distribution, we need to make some decisions first. So I'm gonna use my whiteboard here. So we have some steps that we need to take, steps before making a distribution, or before establishing, or before building the distributions for numerical when we're dealing with quantitative data. The first one is to decide about or determine the number of bins, number of classes. So for that, this is really a very subjective issue, number of bins. Number of bins usually depends on the number of observations, number of data points. And it's usually somewhere between 5 to 20, as the book specifies. In this case, in the audit data file, we're dealing with 20 data points, just 20. This is a very small size data file. So I'm just gonna go with the smallest number here in this range. I'm gonna go with 5. So, when n is large, number of observations, n is large, you're probably gonna go with 20 or even higher number of, more than 20, maybe up to 50, sometimes up to 100 number of bins. If the sample size is small, you may want to go with, if the sample size is small, you may want to go with the smaller number of bins, like 5. In this case, we're going to go with 5. So number of bins. Again, this is a very subjective issue. I'm going to go ahead and take 5 here. The second one, you're going to decide about the bin range. Determine bin non-overlapping bin range, bin limits or bin ranges. So we have data from 12 all the way to 33. And like we already decided, we're gonna divide this range into 5 equal non-overlapping groups. So we're gonna divide this within 2, 3, 4, and 5. And they should be equal, right? This is how we build, how we establish the bin range. So number of bins 5, and what is the bin? So before actually finding the bins, we need to decide about the bin widths. Bin widths is going to be the range divided by number of bins. Range here, 33 minus 12. Maximum minus minimum in the data file. Number of bins, we just decided it to be 5. 33 minus 12, 21. Divided by 5, 4.2. This is what we get for the bin width. And bin width should be, bin width cannot be lower than this. Bin width can be slightly equal or slightly larger than this. This is acceptable. Equal bin width can be equal 4.2 or slightly larger than that, like 4.5 or even 5 should be okay. So I'm gonna go with the exact number here. That's probably easier. So if we go with that, our bins are gonna be, so we're gonna start, if you go with exactly this, you have to start with the minimum. If you go with a slightly larger, you can go a little bit below this. That's also possible. So as you can see, the bins, the number of bins was subjective. This is still, there is some subjectivity here. I mean, you have the minimum value, but you can still play with it. And bins also, you may want to go with the round number. You may want to go with non-round number. You see, so there is still some flexibility in terms of picking the bins. So I'm going to go with exactly 4.2. And if you go with that, you have to always start with the minimum. So 12 to, you need to add this to that, 16.2, 16.2 all the way to 20.4, 24.6, 28.8, and 33. So now we divided the data set, we divided the range into 5 equal bins. Each one of them, the bin width for each one of them is equal, and they're like equal to 4.2, right? 5 equal bins. So this is basically how you build the bins. And now we can go ahead and go with the Excel operations for finding the frequency. But when it comes to Excel, we just need the upper limits of the bins. That's what we need when it comes to Excel. So I go back to Excel here. I just call it the bin range or bin range. So we just, again, only the upper limit. So the first one was 16.2. Next one was 20.4. 24.6, 28.8, and 33. What you need to make sure is that your minimum value should be in the first one. The maximum should be in the last bin. So this is the minimum requirement for building the bins. And you also need to make sure that the size of the bins or the bin widths are equal. Now, we just need to count the number of observations that belong to each one of these bins. For that, there are, again, multiple ways you can do that. I'm going to use, for now, I'm going to use frequency function. That's one way to do that. For frequency function is an array function. So you now need to get familiar with a new concept, array function. We're going to work with multiple array function in this course. This is one of them, frequency function. Array function is when you type a formula once, but the formula get applied to multiple cells at the same time. So that's the difference between a cell formula and an array formula. This is an array formula. I mean, cell formula is like this. You type the formula in one cell and the formula gets applied only in the same cell. Whereas here, I'm gonna type the formula once, but I'm gonna apply it to the whole array here. So I'm gonna start typing frequency. So it asks for two inputs, data array, which is the data file, which is the data set, basically. All these observations, all these year-end audit times, and then bin arrays. Bins array, so you just pick the upper limit of the bins that you established. Once you have that, this is, like I said, this is an array function, so you need to press not enter, but control shift. You need to hold control shift and then press enter. That way the formula gets applied to multiple cells at once. So if you do that, so again, this is an array function. Array function, they need control plus shift plus enter to be run, basically. Array function, what is the array function? Frequency. Frequency is an array function, and for them, you should use, once you type the formula, you should use, I'm gonna do it one more time. I'm just gonna delete this, select the whole thing, equal frequency, data array, comma, bins array, control shift, enter. Or I think if you're working on Mac, it should be command shift enter. So now we have the frequency, and just to show you how the formula is different, you see there are brackets. I didn't type brackets. This shows that these are array function. Again, we typed the formula once, the formula got applied to multiple cells at the same time, right? So that's the frequency. We already know the definition of relative frequency. Relative frequency shows the proportion or percentage of the total observations that are coming from each specific bin. So for that, I need to find the total observation, total number of observation, total frequency, and that would be the sum of frequencies of all the observations, which should be the same as the count of observations, which should be 20, as we know. So relative frequency of each bin divided by the total frequency. And I'm gonna fix the total frequency by adding the dollar signs, and I'm gonna drag it down all the way to the end. Sum of these should be equal to 1 again. We already know that. Sum of the relative frequencies should be equal to 1. All right, so let Let me just type the formula here. The next concept that we're going to deal with now is called cumulative frequency. So cumulative frequency, the definition is the sum of frequencies of all the observations that are less than the upper limit of each bin. So this this absolute frequency shows the frequency of observations or count of observations that are between 12 and 16.2. But cumulative frequencies shows the count of observations that are below 16.2. Since the minimum is 12, so this should be exactly the same as 7. But the next one, cumulative frequency of this one, is going to be the sum of frequencies of all observations that are less than 20.4. So we already have 6 observations that are between 16.2 and 20.4, and we have 7 observations that are below 16.2. So the cumulative frequency here should be sum of 7 and 6, right? The next one, cumulative frequency for the third bin is going to be sum of the 3. The first one is going to be 7, or sum of 7, which is the same thing, and so on, right? I'm going to do this one. I'm going to type the formula one time. This is what you can do. Sum of B10 all the way to B14. So the sum of frequencies of all the observations that are below 33 it's 1. There is one observation that is between 32 and 28.8. 1 plus 2 that is with 2 that are between 20.6 and 28.8 plus 4 that are between these two plus 6 that are between these two plus 7 that are less than 16.2. So if I take the sum of all of them, that's going to give me the cumulative frequency of the last bin. And the cumulative frequency of the last bin is always equal to the count of total count. I can fix this, the origin, the first one, and I can drag the formula upside. So that way, it gives me the cumulative frequency. Also, cumulative frequency of each bin is the same as cumulative frequency of previous bin plus the absolute frequency of the current bin. So 20 is the same as 19 plus 1. 19 is the same as 2 plus 17. 17 is the same as 13 plus 4. 13, 6 plus 7. All right? So this is cumulative frequency. The sum of observations, basically the total count of observations that are below the upper limit of each bin. So that's just the definition of cumulative frequency, right? Now, this is what we have here is called table presentation of distribution or frequency distribution, right? Table representation. Now, if we show it in a graph format, in a basically column chart format, it's called histogram. So for histogram, for histogram, you can use the same frequencies and basically create a column chart. You can do that. You can just go ahead and pick these two, insert a column chart here. Wait, no. You can pick the frequencies, insert column chart, and then instead of the X values, you should have the bins, but this is not how we are going to build it. The way we're gonna do it here, which makes us actually not going to use the frequency function. When you use the histogram tool in Excel, you don't need to use the frequency function anymore. So basically from now on, you don't really type the frequency function. You work with the histogram tool. Now let's just use the histogram tool. If you go to Data tab and Data Analysis here, if you don't see Data Analysis here, you need to add the Analysis tool pack. In order to add that, you need to go to File, Options, Add-ins, press on Manage Excel Add-in, press on the Go button, and then check the Analysis tool pack here, and okay. Once you do that, under the Data group, Data tab, you should see the Analysis group and Data Analysis tool pack. If you're working on a Mac, I believe it's under Tools and Add-ins or Manage Add-ins, something like that. And when you click, you'll see the same window that we just saw, and you just need to, again, check the checkbox for data analysis, and that'll add it on the Data tab. When you open the Data Analysis tool pack, and when you click on histogram, you pick the histogram tool, open the histogram tool, this window comes up. It asks for some inputs and some output options. So for inputs, input range is the range of the data set. So the input range, this data set, and then the bin range is the upper limit of the bins that you need to establish. There's no label, so everything was numerical. All these values, there's no label. I'm not gonna check this one for now. Output range, where you wanna put it, where you want your graph to be displayed. I'm gonna put it here, K2, for example. You have the option to put it in a new worksheet. You have the option to put it in a new, completely new data file. I'm just gonna put it in the same sheet. And then here, make sure to check the chart output. That is the histogram. That is what's going to give you the graph, histogram graph. So just check this chart output and press OK. Once you do that, you'll see it gives you the frequency table, same values that we have here. So you, like I said, you don't really need to use frequency function if you know how to use the histogram tool. And it gives you the histogram graph, the chart, and this is already formatted. So you don't need to do the column chart and then work on the formatting. You already have it. If you don't like this more group, the more bin, you can just take it, and you need to completely remove it from this data set. In order to do that, you can right click on it and press delete, and shift cells left or shift cells up, doesn't really matter here because we don't have anything anything below or to the right of this data file. And this is the histogram that we should have. All right, so this is how we build a histogram. Now, the question here is about the shape of this histogram. This is obviously not a symmetrical graph. This is not a symmetrical histogram, right? This is actually a right skewed histogram, or this histogram, this distribution is skewed to the right side, which means there are a few observations that are far beyond the rest of the majority of the observations. A few observations that are considerably higher than their value. Their values are considerably higher than the majority of the observation, right? So this is called skewed to the right side. I'm just gonna, just to, again, explain the skewness. If I come to the slides here, skewness is about the lack of symmetry, and skewness, I mean, we can just define it through some examples here. This is when we are talking about a symmetric distribution. As you can see, around, all the observations are symmetrically distributed around a mean. And as you can go to the right and to the left, you see the frequency decreases equally if you go to the right or if you go to the left, right? And at some point it gets close to zero. Whereas it may also, if it's not symmetric, if you have, I mean, we're talking right now, we're talking about distributions where there are only one mode, one maximum in the frequency. See, there's one peak here on this graph. So if that is the case, the graph can be skewed to the left, skewed right, skewed to the right side, or symmetric. This is also skewed right side, right? Highly skewed right, as you can see. There are only a few items that are way to the right of the distribution. So the tail is at the right side. The tail is at the right side. The tail is at the left side. Example of this one is, think about it. What variable can you think about that has a left skewed basically distribution? Okay, also think about this one. What factors are, what factors or what variables can you think of that have right skewed distribution? I'm just gonna discuss this one. I mean, income or wealth, this is something that usually is right skewed. There are always a few people with significantly larger percentage, significantly larger amount than most of the people at the bottom side of the, or at the left side of the distribution, right? The majority of the people have, let's say, an income of between 0 to 200,000, but there are some people with revenues over 2, 3, 5 millions a year. The percentage is significantly less than the rest of the people who with the lower ranges. Can you think of any value, any variable with distribution that is skewed left? I didn't think about it. How about I'm just going to name some variables, and you think about the shape of the distribution. How about the height? How about the weight of people? How about the unemployment rate in different counties? How about we already said about the wealth distribution. It's probably this one actually. Income, wealth, and age. How about the grades in exam? How about the GPA? How about the number of children? So think about these examples and try to see if you can identify left skewed and symmetric distribution in realistic variables.